Uh, uh, Concerning the button now, the button issue, I don't know how the button works, so
Okay, how the
that is one
button works.
question. So,
Okay, so this is what I'm going
yes.
to do. I'm going to actually simulate the project right now online. So you'll see how the button works and every other thing that the system does. So it will actually help you with whatever it is you want to write as regards the project. So let me share my screen. I'm going to share my screen with you, and I'm going to uh, simulate your project so that you can actually see how the button works. Hope that's fine with you, Sejiro.
Oh, yes, yeah. I'm
All
okay with
right,
that.
thank you. I'm not sure. I don't know where your project is right now yet. What is the title of your project? I think it is lights control. Uh, uh,
Yeah,
yes. Okay. So let me look for it. Let me look for it so that I can pull it out. Light control. Basics. Several. Hold on, Sejiro, a minute, please.
no problem, sir.
Button.
Trying to.
What I'm going to do is I'm not just going to discuss. I'm not just going to discuss on the button. I'm going to discuss on every other aspect of the project. So let me share my
Okay,
screen.
so
Yes. Let me share my screen. So let's go to share. Let me share screen. I will share my screen with you. Okay. So Sergio, tell me you can actually see my screen.
yeah, I can see the screen now.
All right. Good. So this is what I'm going to do. I'm going to actually run you through a quick introduction of what your project is, or what I've actually designed your project to be, what I have done so far on your project, and how this project is going to actually be of use to you. Now, you told me you wanted a system with which you can actually put a countdown timer on to either put on an appliance. I mean, an appliance is switched on, and while the timer counts down, the appliance goes off. That's very
Yes.
simple. That's very basic. I felt that is actually what you have in your microwave, and that is what is obtainable in some systems around. Now, I felt it
Yes,
would be
yeah,
better if we
yeah.
have something that actually offers something unique and different from that. That's the essence of doing student project or doing projects in the first place. You do not have to replicate what is readily available in the market. The idea is going to be to create something that is unique to you. It does not matter how little, what modification is it you had to it. So this is what I did. What I did was I felt, okay, this is what I can do. Quite a lot of household, for instance, most times when I stay around my office up on the Saturday and Sunday, there are some shops that doesn't open. They don't open on Saturdays and Sundays, but their security lights are always on. All their lights are on. Imagine
Yes.
those stores that sell shoes. Those stores that sell shoes.
Mm.
What you know about those stores is that when they go on Friday or when they leave on Friday, most times all their electronics are on. And then until Monday again before they come back. You can imagine
Yeah.
what distress that can be on an average transformer and
Transformer, yes.
and for PACN. Now it would have been better if they had a system that can turn off their security lights in the day and then put it on again in the night. On the
Nice,
days
yes.
when they are not around. That means on the days when they are not around, like the Saturdays and Sundays. But if they are around on Monday,
Yeah.
because they have displayed their goods, it's easy for them, or it's okay for them to actually display, leave the lights on. So I felt, okay, this is what I can do. Instead of designing just a countdown timer for Sejiro, and it will only benefit Sejiro, this is what I'm going to design a system that will benefit both Sejiro and myself. So how is it going to benefit me? What am I going to do to this system? So I said this. I'm not just going to design a countdown timer. I'm going to design a system that you can actually impute your on time and off time. When I
Okay.
mean input your own time, it means the system first of all must have a
State
digital
time,
clock,
okay.
must have a working digital clock calendar. The system should be able to actually display time, which means when it displays time, it should be able to display minutes, hour, second, and the rest. Now, if you know what time is it in the day, it's easier for you to say, you know what, at this time tomorrow, or at this time again today, or at this time at interval, or at whenever is it that it is this time again. I want you to actually put off
The system
my
should
security lights,
on off.
or
Okay.
then at this time of the day, put them off. So you have in the future of imputing real time, not just countdown timing, real time. You're not just counting down, because another thing you should know about countdown is this. If you are counting down, assuming you have set a system to count down for just 1 hour, and you had actually elapsed 30 minutes, and suddenly NEPA takes light. The issue with the system is that the system will not remember where it was before. If NEPA even restore light 5 minutes after they took that light, it will be difficult for that system to reconcile what time it was at when NEPA took light, and how much time it has wasted, and how much time it has left to elapse. If the system is if the system is designed in such a way that the programmer added or incorporated EEPROM features to the system, to the design. When I mean EEPROM feature, it means that he enabled a system where he enabled a feature where the system can remember what time it was before it went off.
So this is it. So
that's what EEPROM is. EEPROM is electrical, erasable, writable, I think memory or random access memory.
Yeah.
But what you should know about EEPROM is this. You can always just check these details out. What you should know about EEPROM is that whatever you write into it is stored into it. Even if it loses energy, if it loses power, if it loses electricity, the information is always stored, so that when it comes back on, it can continue from where it last stopped.
Yeah, it stops.
That is what EEPROM is. Now, when you are doing any, let me now give you let me give you a better explanation.
Sample.
If you are working on Microsoft Word on your laptop, and you have not saved that job you are doing in your external drive or in a location on your laptop, that job you are doing is actually resident on your RAM.
Yes.
It's on your RAM. If your laptop goes off suddenly, there's a possibility, or there's a very good possibility, that you are going to lose that file. Reason because the file is just on your RAM. It has not been stored in a permanent location or a local drive on your either on an external flash drive or something. It has not been stored. It has not been saved. Now, it is when it is saved that you can put off your computer, come back again, and pick it up at a later time. Even though Microsoft Word has actually now added some features to the application now, so that even if your NEPA goes off, there's a possibility that it will have actually be doing autosave for you. You get my point now. But before the advent of the autosave, what you're actually doing is on your RAM. If you have not saved, if you have not clicked Ctrl S. Now, this is how it happens on the microcontroller too. On the microcontroller, if you do not save any information, maybe a RAM content, a register content, if you don't save it in the external EEPROM, or if you don't save it in the EEPROM, whether external, those are the 24 SC series. Those ones are from Atmel. The serial EEPROM, they are called serial EEPROM, or the internal EEPROM of the microcontroller. If you don't store whatever information you want stored there, if the microcontroller goes off, it doesn't remember those information again. It has to start all over again. So follow the scenario. You have a system that's supposed to count down from 5 to 0, and the system was counting down. I hope you can see my screen. Now, why the system was counting,
I can see it.
The system count down to say 3 before NEPA goes off. If it was supposed to go from 5 to 0 in 5 seconds, which means that it's supposed to spend just 5 seconds counting down from 5 to 0. And then while it has counted down to 3, which means I spent 3 seconds, NEPA took light, or the system went off. And then NEPA did not restore light until after 2 hours. If you have saved this information on the EEPROM, if you put on the system after 2 hours, it will begin its countdown from 3 down to 0.
Okay.
But that is not a real-time system, because NEPA already has robbed you of that time. You couldn't have said this system elapsed in 5 seconds. No, it got to 3 in 3 seconds and got from 3 to 0 in 2 hours. Do you get this scenario? Do you get what I just said now?
Yes.
Should I repeat myself?
You can repeat it there, yeah. I think
this is what I mean. You have a system that's supposed to count down from 5 to 0 in 5 seconds. What it means is that this system is supposed to spend 1 second on each of the counts. Are you with me?
Yeah.
Now, it has counted down to 3. The NEPA took light. or the system went off. And then the system came back on after 2 hours. Now, if you have enabled EEPROM at every count or at every reduction or on the count, what will happen is that the system would remember that the last count it had was 3. It will now begin to count down from 3 down to 0. But you would understand that that is not a real-time countdown. Because it only count down from 5 to 3 in 3 seconds and went from 3 to 0 in 2 hours.
2 hours, yes.
Because that was the time. Because that was not the time. Because that was the time NEPA took light and brought back the light. Are you with me? But with this particular system that we are talking about, with the one I'm designing for you, the one you're actually seeing on the screen, if you set it to count down from between 5 to 0 in 5 seconds, if NEPA takes light why it was at 3, if NEPA brings light immediately 5 minutes after or a minute after, the system will not do anything again because the countdown time has elapsed.
Okay.
It has elapsed. So this is what it means. If you say I want my appliance to come on at 6:30 p.m. and I want my appliance to go off at 7
at 6:30.
Okay, let's say 7 o'clock. At 7 o'clock a.m.
Oh.
So you wanted to do that, and you set it into it. If there was no light at 6:30 p.m., there's no light.
Okay.
But if NEPA brings light anytime before 7 a.m. the next day, your system will give you light. And let me not tell you the good part of it. Let's assume that NEPA did not bring light until it was past 7 a.m. And they brought light at maybe 7:30 a.m. That system will not put on your appliance. Because before it put on the appliance, it will go and check at what time am I asked to come on and go off. I'm asked to come on I'm asked to go off at 7 o'clock a.m. 7 a.m. Now it is 7:30. Why should I put on anything? So it won't do it. What it means is this. But the reason the system can actually do that is because it is relying on a real-time clock calendar feature that it has. What it means is that there is no light, there is a backup battery in your system that is keeping date and time for you.
Okay.
Why there's no light on the system? Why there's no light from NEPA, from PACN, from your generator? The system has an inbuilt battery that is keeping date and time for you. It's such that anytime it comes on, all it does need to do is this. Is you ask yourself, at what time am I asked to come on and go off? Okay? What is the time now?
Yeah.
So what should I do? So it is when it compares what time it is in the day and what time is being set in its memory to come on and go off, that is when it can actually work perfectly. That is the system you have. That is what I'm offering you.
Okay.
Now, for this system to be able to work accurately and perfectly for you, you will need to have a user interface where you can set the time and date in the event that the time and date is wrong. Because if the system's time and date is wrong, whatever time and date you have set to it to come on and go will be wrong.
Yes.
Are you with me? So this system is not a countdown timer. It is not a countdown timer. It is a system with a real-time clock calendar feature that also accepts input from the user to set their preference of an on time and off time, with which they use in controlling the output of a relay that powers a load. So let me begin to break it down in a bit, or let me begin to explain the circuit diagram you have. Guess what you have? You have PIC microcontroller. That is the core of the design. Don't forget the block diagram I sent to you some days ago. You had this, you had power, you had input. I told you that the microcontroller is a processor. Of course, it's more than a processor because it had other things that a microprocessor does not. That the microprocessor does not have. I'm glad you read it. I'm glad I saw the snippets you sent to me. So it is a controller. It does processing, arithmetic logic unit. It has input output feature. It has timers. It has RAM. It has ROM. It has program memory. It has and it can actually interface with quite a lot of things. Of course, it becomes like the brain, or it is the brain, the middleman between your input and then your output. That is what it is. So that is your microcontroller. This is it. You have an LCD screen.
Yeah.
The LCD screen, of course, is supposed to be interactive. Your mobile phone has a screen, it's interactive, so you know what you are doing at every point in time. Your television is interactive. You can see what you expect to see. If what you are seeing is not what you want to see, what do? You change the channel. And when you change the channel, you can see that the channel changes. So it's interactive. So the screen is supposed to create a user interactive or a user graphic interactive feature. Then you have a buzzer. The system actually has an alarm in it. The essence of the alarm is this: if you set an on time and an off time, I expect that the system is supposed to actually notify you every time it has carried out its operation. That is just it. It's such that even while you are sleeping, while you are while you actually around the house or around where the system is installed, every time it carries out its operation, like the on time, like when it on an appliance, like when it offs an appliance, it gives a notification. That notification is just to get you informed that whatever it is I've set the system to do, it is doing it. Are you with me? That is what the alarm notification is there for. Okay? The system then has this. If you look at this assembly, let me zoom around it so you can see it. This assembly is the output assembly. This is where your home appliance is connected. If you look at it, you have a relay. This is a relay. This is a 10 amps relay.
Yeah, I saw a relay.
Now, the 10 amps relay, if you look at it, what's the implication of having a 10 amps relay? The implication of having a 10 amps relay is that since the relay itself can stand 240 volts at 10 amps, it means this system can adequately power a load of 2.4 kVA for you. Now, 2.4 kV. Let me now do a very simple mathematics. If this system was used to power bulbs, if this system was used to control bulbs, I mean bulbs in the house.
Yeah, NEPA bulbs, yeah.
Or NEPA bulbs. The highest NEPA bulb, wattage of NEPA bulb you can get in the market is going to be like 100 watts. That is if you are not using a prepaid meter.
Yes.
Are you with me?
Yes.
Now, you have a power formula. They say power is IV. IV or VI. Well, okay, good. Now, if I told you that this system can stand I told you this system can stand 2.4 kVA worth of load. I told you that. And that's what you can power at maximum. And the question is, if you have 100 watts of bulbs, how many bulbs will you have on it?
Like if you have 100 watts.
Yes.
Of bulbs
100 watts of bulb. Yes, on relay. How many 100 watts of bulb can you have?
Just divide now.
Just divide. Thank you very much. So what you need to do is just divide. We already know that this guy can stand 2,400. Say what? Just say 2,400. Are you with me? Divided by your 100 watts.
I'm with you.
It means that you'll be able to connect 2,400 watt bulbs on that relay. Did you get it? 2,400 watt bulbs on the system. How many houses or how many compound has 24 bulbs?
24 bulbs. What is next? Did
you get it? What it means is that this system itself can actually serve more than a compound. It can serve an estate. It can serve a street. It can serve different streets. And all their security lights are going to come in. Maybe, of course, there might be bulbs that actually consume more power, more wattage than 100 watts. Of course. But all you need to do is just divide the number of watts, that watts rating, from the total number of watts this relay can stand, and divide it. And then you get the number of such bulbs you can actually put on your system. The good part is this: I have made two outputs available. Two outputs. What it means is that you have channel 1, you have channel 2.
Channel 2.
Is this clear? So this is the relay. This assembly or this what you're actually seeing right now is the relay assembly. The relay circuitries that will be responsible for supplying voltage to your bulbs, your security bulbs.
Your appliance.
And your appliance, or wherever you connect to. So it can be bulbs, it can be appliance, it could be pressing machine, it can be pressing iron, it could even be your air conditioner. Put your air conditioner on it. So long as the power rating of your air conditioner falls below plus or minus 10, minus 10% of the total power rating of this relay. Does that make sense? So, okay, this meeting we're in 10. This meeting we're in 10 minutes. Okay, no wahala. Okay, so quickly before the meeting ends, I've shown you the microcontroller. I've shown you the display, the screen. I've shown you the load. Another thing that you have is the way a user can actually interact with the system, which is through these 3 buttons, and which is what you want to see, which of course I'm actually going to simulate for you. So with this button, a user goes into the menu, chooses whatever it is they want to do. And I've designed a system so that there are a few things you can do. When we get into the internal operation, I'll show you. I believe you can check real-time clock, you can check what time it is, you can check your on time, your off time, and then you can modify, you can edit your on time, off time. You can also set the time. Imagine a situation where the battery, the internal CMOS battery of the real-time clock calendar IC is bad. It's going to actually return the time, but it's going to actually backdate it and make the time wrong. It's not going to be in real time, it's not going to be the time of the day. These buttons are with what or how you actually input what the new time should be, or what the edit is how you actually edit the time feature of the system. Exactly. Now, another thing that you find the system will have, the system is actually going to have a real-time clock calendar module. Usually, the idea was actually supposed to of course, the IC we are using is the DS1307 IC. But of course, because I was looking at the rigor of having designed our own circuitries around it, I actually decided to buy the module and fix it. So you're actually going to be seeing a real-time clock calendar module that's actually going to be fixed on it. Now, this is your power session. This is the power session. And quickly, I could just explain what this your power session is before we actually end this class. So this is the power session. How does it work? You get a step-down transformer, a main step-down transformer that steps down 220 to 12 volts. That 12 volts is actually imputed into this terminal block. That voltage goes into a switch. This is a power switch. And then before it goes into your bridge rectification, your bridge rectifiers. So this is a bridge rectifier. Of course, we have used 4 diodes to actually achieve the same result or function going to the market to get a bridge rectifier will have done. So we use this. The output from that transformer, of course, the moment the AC goes into this bridge rectifier, this bridge rectifier converts that output to DC. But the DC has ripple. The AC property still has it. It's a pulsating DC. This capacitor, 1000 microfarad, 25 volts, will be used to actually smoothing out this ripple before it is sent into a voltage regulator, a 5 volt voltage regulator, and then the output of that voltage regulator drops it down for us to 5 volts, and that output is filtered again with an 100 microfarad 16 volt microcontroller before it is then sent into everywhere where 5 volts is needed. Wherever you see VDD, that's where 5 volts is needed. Wherever you see VIN, that's where 12 volts is needed, or less than 12 volts. And then before it now goes into a variable resistor that is used for your contrast control of your liquid crystal display. This is as simple as what this power supply should do. Of course, I know I glossed through that. I know I just ran through that. Or when the project is actually done, or when it's eventually done, we'll run through all of these things again in details and explain to ourselves what this project is. So this is what I'm going to do. I'm going to actually pause this class right now. I'm going to send you a link again so that you can continue this class where I now simulate for you how this project works, what it does, how you're going to go about doing the settings, editing the functions, using the push buttons that you want to see, and then you can make sense of it and then get something written for your supervisor. Hope this makes sense. Hope it makes sense.
Yeah. But
I hope you learned some.
concer-
We are coming back
concerning the
online. We are coming back online.
okay, 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 okay,
Let's just
okay.
stop this class and then start it again. All right.
All right,
Sorry.
all right.
Thank you. Okay.